A meeting of minds, art and colour science. Colour is an amazing phenomenon. What other topic covers such a wide range of interests, from the arts to biology and botany, chemistry, design, geology, to language, mathematics, photography, philosophy, vision, zoology, and much, much more. It is imperative in a manufacturing environment, all departments across the organisation, from research and development, design, marketing, production, purchasing, sales and technical service, can communicate with each other in the same colour language. CMS is designed to cross these bridges. Colour Made Simple, an online colour course for visual colour assessment and instrumental colour measurement, including interactive colour exercises. A course developed by Nick Harkness, Stephen Westland and Vien Chung. There are 18 chapters in CMS, and in keeping with the theme of a meeting of minds, they are split 50-50 between the world of art and design and world of colour science. Today's webinar is a snapshot of the topics covered in CMS. I would like to commence with a statement from CIE Committee 116, which met in 1995. Many industries employ colouring processes designed to enhance colour uniformity, colour recognition or aesthetic appeal. The producer must deliver a product of the desired colour with its variation controlled to an extent appropriate for the product's use and customers' expectations. There are many variables which influence colour difference assessment, namely material characteristics, the viewing environment and psychological factors. A full understanding of colour difference perception requires a knowledge of the influence of all of these factors. Our seminar endeavours to provide this understanding. The automotive industry is a peer in the realm of colour. Not only is the industry a market leader in terms of colour technology and marketing, it is also aligned with 3 other industries, paint, pigments and plastics, which combined are leaders in colour quality in manufacturing. The influence also extends to urban myths, true or false. The Rolls-Royce logo changed from red to black in 1910 after the death of Charles Rolls. Colour is intrinsic to industrial design, colour trends and colour naming. For example, British Racing Green. Comparing the colour numbers to the visual experience. A meaningful colour measurement system must bridge the gap between the psychology of visual colour perception and the physics of spectroscopy. Simultaneous contrast and afterimage clearly have an effect on the perceived colour, whereas the numbers don't change. The range in interest in colour is extraordinary. From the arts, in this case a dynamic screen print by Albert Irvin, an English expressionist abstract artist, and Sunflowers by Van Gogh. Mathematics and physics. Colour scientists have developed colour difference equations to mathematically describe as closely as possible as to how we perceive differences between colours which are close matches. Here we have the equations for the latest CIE DE 2000. There is often debate and disagreement between academic disciplines as to the role of colour, but also within academic disciplines, for example from Kant. In painting, sculpture and in fact in all the formative arts, in architecture and horticulture, so far the fine arts, the design is what is essential. Here it is not what gratifies in sensation, but merely what pleases in form. That is the fundamental prerequisite of taste. The colours which may give brilliancy to the sketch are part of the charm. They may no doubt in their own way enliven the object for sensation, but make it really worth looking at and beautiful they cannot. Whereas from Hegel, shape, distance, boundaries, contours, in short all the spatial relations and differences of object appearing in space are produced in paintings only by colour. Albers related colours in the Goethe triangle to moods, in this case serene. From the World of Literature, a quotation from Cod by Mark Kurlansky. The town of Lunenburg in Nova Scotia was built on a hill running down to a sheltered harbour. On one of the upper streets stands a Presbyterian church with a huge gilded cod on its weather vane. Along the waterfront, the wooden shingled houses are brick red, a colour that originally came from mixing clay with cod liver oil to protect the wood against the salt of the waterfront. It is the look of Nova Scotia, brick red, dark green pine and charcoal sea. At twilight there is a switch from cone photopic to rod scotopic vision, which produces a change in the perceived intensity of the blue and red regions of the spectrum. Rod vision has a mean sensitivity towards the shorter wavelengths of sunlight, namely blue. And here we have an example with the jacaranda tree, noon when the colour appears to be more reddish compared to the early evening when it appears to be more bluish. There are many influences on colour perception. For example, the Ernst Mach bands. We have 6 uniform rectangles of varying lightness and chromaticness. But once these rectangles are aligned directly alongside each other, we observe a waviness of light to dark across each rectangle. Another example is the corn-sweet illusion, also known as the Craik-O'Brien corn-sweet illusion, as described by Tom Cornsweet in the 1960s. The sample on the left appears to be lighter and less chromatic than the sample on the right. However, if a border is placed between the two door rounds, they now appear to be the same. Colours are modified by adjacent colours. The blue background on the left looks lighter and less chromatic than the blue background on the right, but viewed under the same conditions, the two blues will appear to be the same. Joseph Albers wrote in his Interaction of Colour, "If one says red, the name of the colour, and there are 50 people listening, it can be expected there will be 50 reds in their minds, and one can be sure that all of these will be very different." Purple is a reddish blue or a bluish red, and orange is a yellowish red or a reddish yellow. Red, however, cannot be a purplish orange, nor an orangish purple. Green, as eloquently proposed by Wittgenstein. It might be thought to be wrong to include green, as it is considered to be a mixture between blue and yellow. However, while a yellowish red or a yellowish green are possible, perception does not allow a bluish yellow nor a yellowish blue. In fact, a pure green is possible, which has neither a bluishness nor yellowishness. Monochromes are colours which lie in the same hue triangle, but vary in lightness and chromaticness. Here we see the famous colour wheel of Johannes Itton, one of the greatest teachers of colour theory. The colour wheel is produced by mixing the 3 primary colours of subtractive colour mixing, but more on these topics later. Dyadic hues. 2 colours, such as colours on opposite sides of the colour wheel, which are considered to be complementary colours, for example red and green, and in this case blue and orange. The striking impact of blue and orange hues in this powerful image of the Monasterio de Santa Catalina in Arequipa, Peru. Triadic or analogous hues can lie between primaries, in this case yellow and red, or between secondaries, between green and purple. Robert Boyle, the Anglo-Irish chemist, generally considered to be the first of modern chemists, and known particularly for Boyle's law, which states that the pressure and volume of a gas have an inverse relationship when temperature is held constant. Like many of his contemporaries, Robert Boyle also took a great interest in the study of colour. There are but few simple and primary colours, if I may so call them, from whose various compositions all the rest do as it were result. For though painters can imitate the hues, though not always the splendour of those numberless differing colours that are to be met within the works of nature and of art, I have not yet found that to exhibit this strange variety they need employ any more than white and black, and red, and blue and yellow, and these variously compounded, and if I may so speak, decompounded, being sufficient to exhibit a variety and number of colours. I do not think that the modern colourist would completely agree that one can obtain a complete colour palette to meet current customer expectations with just white, black, red, blue and yellow. Generally, paint manufacturers will use 12 to 14 colourants in order to offer the many thousands of colour options they provide for their customers. Robert Boyle was referring to what we were all taught in art classes in school, that the three primaries of paint are red, blue and yellow, and their secondaries, orange, green and purple. In 2003, I was fortunate to be able to attend the NCS summer school held in Gripsholm, Sweden. I was the only colour scientist out of 25 attendees. The remainder were from design, industrial and interior. We all had a project to complete, and I decided to review the colour wheels of art, physiology, perception and science. My first attempt was the colour wheel of art based on the primaries of red, blue and yellow. For those of you who are colour matchers, you will know that this was courting with disaster. Perhaps an adequate orange, but the purple, well, more like mud, and a green like olive. They were both well off my expectations. So let us go back to first principles. There are two sets of primaries, the additive primaries and the subtractive primaries. What do we mean by additive primaries? These are the primaries of light, red, green and blue. The primaries of subtractive colour mixing, the world of paints and pigments, are cyan, magenta and yellow, and not red, blue and yellow. Learn more about primaries in CMS. So even with my limited colour mixing skills, I was able to produce a satisfactory colour wheel when based on cyan, magenta and yellow. Aristotle, simple colours are the proper colours of the elements, fire, air, water and earth. Black mixed with sunlight and firelight turns crimson. Aristotle believed yellow came out of lightness and blue out of darkness. This was recognised by Leonardo da Vinci. In his treatise on painting he wrote, "The first of all simple colours is white, though philosophers will not acknowledge either white or black to be colours, because the first is the cause or the receiver of colours, and the other totally deprived of them. But as painters we cannot do without either. We shall place them among the others, and according to this order of things, white will be the first, yellow the second, green the third, blue the fourth, red the fifth, and black the sixth. We shall set down white for the representative of light, without which no colour can be seen, yellow for earth, green for water, blue for air, red for fire, and black for total darkness." In 1878, the psychologist Ewald Hering proposed his opponent colour theory of colour vision, based on four psychological primaries, red, green, yellow and blue, where red to green and yellow to blue have a postulated opponent psychological relationship. Hering's hypothesis appears initially to be in conflict with those of Thomas Young and Helmholtz, which are based on three primaries of colour vision, red, green and blue. Both the latter are in fact partially correct, and contribute to our current understanding of the mechanism of colour vision, namely Young and Helmholtz at the first stage of the colour vision process, the cone level, and Hering at the second or perceptual stage. Hering wrote that if we imagine a clear red of a specific hue placed at the corner of a triangle, a completely pure white at the second corner, and a completely pure black at the third corner, then all possible transitions from clear red to pure white can be arranged along the line from red to white, and all transitions between clear red and pure black along the line connecting red and black. As the distance from clear red increases, the colours thus ordered would be continuously more veiled by white on one side and by black on the other, until finally all traces of redness vanished into pure white or pure black. Hearing's triangles, which rotate over all hues with the achromatic axis at the centre, make an important contribution to the concept of three-dimensional colour space. C-Lab Colour Space, L star, A star, B star, was published in 1976 based on the work of many researchers, including Adams, Hunter, Judd, McAdam, Mueller, Nickerson, Billmeyer and Saltzman. The rationale of C-Lab Colour Space includes features of Hearing's opponent colour theory, the three-dimensionality of colour space outlined by Runge, and the concept of 6 pure elementary colours, white, black, blue, green, yellow and red, as proposed by Da Vinci. The C-Lab axes are L star, lightness, A star, the red-green opponent axis, with positive A being red and negative A being green, and B star, the blue-yellow opponent axis, where negative B is blue and positive B is yellow. CIE is based on Munsell, which has 5 primaries, red, blue, green, yellow and purple. And to accommodate the purple in CIE colour space, the pure visual red is displaced by 22.5 degrees, and the red of CIE is a magenta shade or a bluish red, rather than a pure visual red. On the opposite side of the colour wheel, pure visual green is similarly displaced by 22.5 degrees, and the green of CI Lab is a bluish green. The blue of C Lab is a reddish blue, and the yellow is a greenish yellow. One should be mindful when reviewing A star and B star values of a colour that these are based on colour axes of magenta to blue-green and ultramarine to greenish-yellow. The definition of CIE L star, lightness or luminous reflectance, is one of the most difficult concepts to grasp perceptually. Lightness is often referred to as brightness. A colour's lightness is a function of the total amount of visible light which is reflected from the coloured object. It is helpful to compare lightness in terms of a grayscale and superimpose this concept on a colour. Expressions such as saturation and chromaticness refer to the colour sensation, which is experienced, or alternatively the colourfulness of an object. They are independent of lightness, but both influence our perceptions of the nature of a colour. Numbers and visual, do they agree? The need for additional colour difference equations. In this schematic we have a sphere geometry with diffuse illumination. The diffused illumination is provided by the barium sulfate coating within the sphere. The 8 degree is the angle at which the detector is set from the normal. In this case, the sample is being measured with the specular component included, which means that the spectrophotometer is measuring the inherent colour irrespective of the surface appearance, gloss versus matte. For effect coatings, a greater number of measurements are required to replicate the light and dark flop and also the colour flop, the change in colour or colour travel as the viewing angle changes. The multiple angles are required in order to measure the colour travel of the effect pigments as the observer angle changes. The colour difference for effect pigments is now defined by delta E prime effect, which is a combination of delta E prime AB and delta E prime CH. For measuring the colour of samples which are immeasurable using conventional spectrophotometers due to size or shape, digital imaging is an option, such as the Digi-Eye from Veridvide. A glossy sample which has the same inherent colour as a matte sample will appear to be more chromatic and darker than the matte sample. The selection of instrument geometry has an impact on the results that are obtained, be it specular component included or specular component excluded. Spectral reflectance curves are very useful tools for the colour formulator to help them make the correct decisions regarding colour mixes. In this case we see two reflectance curves which have many crossover points, and this is a sure sign that there are going to be issues with metamerism as the illuminant changes. Spectral reflectance curves are also very useful in determining colour strength. For optimum pigment performance, the pigment particles should be reduced to their primary pigment particle size by fine milling, which breaks down the pigment aggregates and agglomerates. Flocculation is the recombination of dispersed pigment particles that were not properly stabilized in the pigment dispersion, resulting in loss of colour strength. If the colour strength, or chroma, of the coating increases when the paint drawdown is rubbed with your finger, then there are flocculation issues. Having fine milled the pigment aggregates down to the primary pigment particle size, the last thing you want is for those pigment particles to re-agglomerate, losing colour strength. In this case, the chromatic strength is calculated at 420 nanometers, the wavelength of maximum absorption. There are three approaches when it comes to colour matching: single constant for dyes and transparent systems, two constant for opaque materials, and multiflux for translucent materials. The Kabel-Kamunck equation applied to a mixture of dye stuffs. A typical series of dye stuff reductions, in this case for a red dye. Because Kabel-Kamunck theory assumes that there is not a refractive index change, measured reflectance is converted to internal reflectance using the Saunderson correction. The Kabel-Kamunck equation for a mixture of opaque colorants, in this case a red and a yellow with a touch of white and a touch of black to give us orange. Coming soon to the short course series, Quality Control Procedures including Computer Colour Matching Theory. There are three components to computer colour matching: the colorant selection, formula prediction and correction. And we have the choice of two algorithms: spectral matching or colorimetric matching. Complementary colours are colours which sit on opposite sides of the colour wheel. When complementary colours are mixed together and tinted with white, they produce very subtle shades of grey. When two secondary colours are mixed together and the mixture tinted with white, there will be a dominant primary. For example, with green and orange, the dominant primary is yellow. The following method of colour matching was presented by Dr. Jean Pretorius at an International Colour Day meeting in Sydney in 2018. It is based on the original teaching by Frank Riley, leaning heavily on Munsell, with versions presented by contemporary realist artists and teachers such as Graydon Parrish and David Briggs. First, select two paints or colorants that bracket the hue of the target colour, preferably both having higher chroma than the target. Adjust the value or nuance of these paints or colorants individually to match the value nuance of the target colour. For this value nuance adjustment, neutrals are used, typically white and a black. Both of these can however cause hue shifts, which means for darkening yellows and reds, a burnt umber alongside the black may be required. The triadic analogous hues of art, perception and science compared, in this case between the primaries of yellow and red, with orange in the centre, giving a very warm impression. CMS crosses boundaries. Art meets science, online, anywhere and at any time. The CMS full course is suitable for personnel from research and development, production, technical service, purchasing, sales and marketing, and design. For those who are not interested in the aesthetic side of colour, we have CMS for instrumental colour measurement, and those who do not want to see too many equations, we have CMS for visual colour assessment. To recap, there are 18 chapters available in the full CMS course. Also available are 5 short refresher courses: Origins of C-Lab, Colour Harmony and Terminology, Influences on Colour Perception, Additional Colour Difference Equations, and Colour Quality Control Procedures. For these short courses, there are no interactive colour exercises. A meaningful colour measurement system must bridge the gap between the psychology of visual colour perception and the physics of spectroscopy. For more information, sign up for Colour Made Simple for visual colour assessment and instrumental colour measurement.